All right, let's get started. Our next session will be taught by Jay Budzik. He is the Chief Technology Officer at ZestFinance. ZestFinance is a software company that helps banks and lenders build, run, and monitor fully explainable machine learning underwriting models. As CTO, Jay oversees Zest product and engineering teams. His passion for inventing new technologies, particularly in data mining and AI, has played a central role throughout his career. Before joining Zest, he held varied positions, including founding an AI enterprise search company, helping major media organizations apply AI and machine learning to expand their audiences and revenue, and developed systems that process tens of trillions of data points. Jay has a Ph.D. in computer science from Northwestern University. Please join me in welcoming Jay for his session, Deploying Radically Transparent Machine Learning Models.
Thank you. Hi, everyone. Thanks for joining today. So I'm going to talk about radically transparent AI models. So this is kind of like a misnomer, right? Everybody knows that ML is a black box and that you can't explain it and it's not safe to use in credit, right? Well, I'm going to here to debunk that myth. And then also, everybody knows that AI models are biased and that they're going to further and amplify the bias in the data, and you can't use them safely without exposing yourself to lots of risk from bias, right? Actually, that's not the case either. So this is a story in 3 chapters. Chapter 1 is about the fantastic performance that you could expect from switching from a traditional modeling framework to machine learning in your credit risk modeling function. We've seen fantastic results across the board, no matter what product, what size of business, what type of loan tenor you're talking about. You'd have short-term personal loans or 30-year mortgages, and machine learning credit risk models simply outperform the type of risk predictions that you get from a logistic regression framework or a traditional credit risk scorecard that you might be using. And so these results are really exciting, but you say, well, so how do you generate all that lift? Well, when you compare an ML model versus a regular model, you can look at sort of what populations each model is approving, see where they agree and where they disagree, and then project forward sort of what economic benefits you might expect. So this is a case study from a very small auto lending business, about $100 million portfolio. And in this case, we built an ML model as a challenger to the champion logistic regression scorecard. We saw the models agreed that on 63% of the population, both models say approve these 63%. But within that common approval population, the machine learning model is better able to rank order the risk. And so what you get is this really nice effect of better pricing. So if I take the lowest risk consumers and I offer them a more competitive rate, they're going to be more likely to take my loan. And so as a result, I get more good consumers into my portfolio. And as a result, I have less charge-offs because the distribution changes. Likewise, for the populations that the models disagree on, these swap-ins, you can see what's happening is that I'm choosing more good borrowers as a result of the machine learning model, and I'm denying more bad borrowers. And so as a result, I reduce my losses from defaults. And so charge-offs can go down. So you get this sort of double effect. I get better risk-based pricing for those folks that both models would approve, and hence better profitability from higher booking rates. And then from the swap populations, I get lower credit default risk. And so I'm making more money as a result. So about $17 million on this $100 million prime portfolio that might be sort of typical of a credit union, a small credit union's indirect auto lending business. So that's cool. But in financial services, we kind of have a high bar. We have to explain why all of the models make each decision to the consumers. If we're going to deny them, they need to get accurate reasons as to why they were denied. We have to make sure that the model development is fully documented, that we understand which variables are using the model, how they contribute to the model score, how the model score varies across a range of different input variables. And we have to make sure that the models aren't biased. In fact, credit is kind of the highest stakes AI application in the business world. Maybe medicine is higher stakes because it's life and death, but these types of decisions around whether or not someone gets a car so they can go to work, or whether or not they get a home so that they can live in their community and plant roots, is kind of a life-changing event for people. And if you make the wrong set of lending decisions, you can get your institution into quite a lot of trouble. And so we've been focused at ZestFinance on developing the tools that enable banks and other lenders to apply machine learning safely and not get their names in the paper like these guys did. So chapter 2, robust explainability is the key to safely applying machine learning. So you got to know why the model's making each and every decision. You've got to be comfortable that the model isn't making biased decisions, and you've got to be able to explain why you think so to your regulators and to your executives. So in a way, machine learning's strengths are its greatest weaknesses when you consider them from a model risk management perspective. A traditional model might consider only a handful of variables, a couple dozen, 40, 50, maybe 100, right? Machine learning model can predict on the basis of thousands of variables. We have one model in production that does 2,200 variables. But that means that you have to document all 2,200 of those variables in your model development documentation. The validation team has to consider the impact of those variables across a range of inputs for your model. There's a lot more work to be done as a result of having more variables in the model. You also have to guard against overfitting and all the other things that machine learning practitioners do on a regular basis. Likewise, most traditional models are based on a linear formula that's in the set of coefficients times an input variable. Those models are pretty easy to understand. If I move this variable up by 5, the coefficient says I'm going to multiply it by 0.2, and this is the impact on the model score. I can do that on a whiteboard or with my calculator. With a machine learning model, you're actually modeling the interactions between all of the variables. And so a change in one variable can impact the model score in a non-straightforward way. And so those interactions make the model harder to explain. You have to use an appropriate method to understand how those interactions play out throughout your model development and model validation lifecycle. So those same interactions help the model become more predictive, because now it can understand the relationships between various variables and how they impact the risk, but they also make the model harder to explain. Likewise, the relatively straightforward math used in a linear model is pretty easy to understand. When you start taking neural networks and gradient-boosted trees and support vector machines and radial basis functions and the like, and combining them into ensembles using a neural network to ensemble and then passing them through a smooth DCDF in order to generate a likelihood on the output, that starts to become a very complex mess of math that is difficult to untangle, and so you need the right tools in order to be able to do that. So what do we do about all this? We carefully follow the model risk management guidance. During model development, we document the techniques. We make sure that we understand how each variable is sourced, how it behaves over time, whether it's actually safe to use in the model. We document all of the model tuning parameters that are used and the decisions that are made by modelers during the process. Make sure that an independent team can validate the model, rebuild it from the data and the model documentation. And then we make sure that the model is appropriately monitored using a method that matches the modeling technique that was in use. So, machine learning models that do all these interactions, you need a monitoring method that monitors for multivariate interactions as well. But none of this stuff matters, even if you do go through all the paces and fill out all the forms and do all of the model risk documentation. None of it matters if the math is wrong. So if you think your model is doing one thing when in reality it's doing another, you could fill out all the forms correctly and run your business straight into a wall. And so it's important that as you consider generating one of these 150-page model development documents to comply with the OCC 2011-12 or Fed SR 11.7 guidance on model risk management, that you have the right math powering the explainability behind it, because the document is sort of useless if it doesn't contain the right information. Likewise, when you go put one of these models into production, it's important to make sure that you have a monitor that's actually capturing what's going on in the world. So this is a chart comparing two monitoring methods. The orange line is the ML monitoring method that captures multivariate interactions in the input variables. And the blue line is your PSI score. So the industry standard way of comparing distributions and deciding whether or not the model needs to be recalibrated. Now you'll see that the orange line is ticking up quite a lot here in Q4 of 2018, whereas the blue one is kind of steady. So if you had relied on the blue one, you would have missed this change in character of the applicant pool that is indicating that the model has no statistical support for that population. It's saying, I'm seeing new stuff that I've never seen before. Danger, danger, please take a look at what's going on here. That's from one of our customers who was in an economy that experienced a 60% devaluation of the currency in Q4 of that year. So it's kind of validating that the model monitors picked up on the change in character of the applicants that was due to the rapid devaluation of the currency. Likewise, the right explainability math can keep you out of trouble. So this is a two-way interaction plot that shows the interaction of two variables with respect to default risk. The first variable is your car mileage. It's an auto lending example. And the second is whether or not you live in state 47, which happens to be Nevada in this data set. So it turns out that state 47 and high mileage is a pretty good predictor of default risk. But unfortunately, it's also a pretty good predictor of whether you're African American. And so having the right explainability math allows you to uncover these types of relationships in the model that the model came up with, and make sure that they're safe from a regulatory and ethics perspective. So chapter 3. With sound mathematics and the right tools, ML can help you make more profitable, fair, and transparent credit decisions. So our goal, I spend all my life on this these days, is to understand how this score of 0.71 on the right is generated by a machine learning model. I want to decompose the 0.71 in terms of the input variables that are used by the model. Right, so if I think you have a very high likelihood of default, and I'm going to deny you, I need to explain what's the difference between the approved borrower score or the approved borrower and you. In terms of these input variables. And I need to quantify with very great precision what is driving this difference in score. And I need to do that for a lot of different reasons. One, I need to give you an accurate adverse action notice that says why you were denied that card you were just applying for. I need to quantify the impact of each variable across populations so that I can say, well, the slightly lower African American approval rate is due to these factors, and those factors aren't racist. I need to do and I need to do a good job of understanding the model risks so that I can comply with regulation. So this is relatively straightforward to do with linear models. I can read off the coefficients in the regression equation and give you a pretty good sense of what's driving the model score, a difference in score. For a machine learning model that's a deep neural network or a gradient boosted tree or an ensemble of those different types of models, again, creating that mathematical mess, this is much harder to sort out. And so there are a lot of people working on machine learning explainability. We've seen a really big uptick in papers published every year on the subject, which is a good thing because it means that folks are taking this problem seriously in academia. But it's also a bad thing because it kind of makes ML explainability seem like the Wild West. So which one of these methods is the right method to use? What are we what should we agree is the truth? These are all sort of open questions. Yeah, you can test the accuracy of ML explainability techniques against a ground truth if you believe in the mathematics of game theory. And so we've done that here on this chart for several methods. We took a neural network and fit it to a very simple data set in 2 variables with 2 classes. It got a very high AUC because it's a very simple modeling problem. And so that model that it generated should be really simple to explain, right? So if you use a technique like leave one covariate out, which sort of substitutes missing for one of the columns in the input data set, unfortunately, that still doesn't get it right. You end up with this really crazy squiggly plot where you'd like to see a straight line. If you use permutation feature importance, which is a common tool that's available in lots of ML platforms, and shuffle each column to see whether the model score changes, well, you get the plot in the upper right, which is all over the place. And then if you use Lime, depending on your choice of hyperparameters, you can end up with these weird blotchy spots. The right mathematics, the type that we use in our tools, generates this nice correlation with the true baseline. Yeah?
What is the X and Y?
Those are the Spearman correlations between the 2 methods. So you want agreement. So the 2 methods that we're varying on the x-axis are the Shapley value, which is the game theoretic baseline we're using in the study, and the y-axis is the value generated by the explainability method under study. So what you see in the lower right is that the XAML contributions agree completely with the Shapley values that were generated, or almost completely. Does that make sense? Mm-hmm. Okay. So kind of the way that you get there is that you rely on these great mathematicians. So Shapley was a game theorist out of Rand and then UCLA, local hero. We're from Los Angeles. Generated a bunch of work on assessing the impact of an individual player in a multiplayer cooperative game. So you think of a machine learning model as like a game. The outcome of the game is the machine learning model score, and the players in the game are the variables. And so Shapley gives a formula that obeys a very small set of reasonable axioms and uniquely defines credit assignment for atomic games. He and his collaborator, Aumann at a Technion in Israel, developed an additional method called Aumann-Shapley, that allows you to evaluate infinitesimal games. Now, Almond Shapley has this limitation, which is that it requires the underlying functions under analysis be everywhere differentiable. So that kind of doesn't work for tree-based models that have jump discontinuities. And so we need the tools of measure theory, introduced by our friend Lebesgue, to analyze those very ill-defined functions. And so we leverage those tools in much the same way that another local hero, Richard Feynman, did to explain quantum mechanical effects. So if you sort of sift through all of that work and find the right mathematics, it actually turns out that these guys figured this out decades ago. So the cool thing is, once you get explainability right, you can do really amazing things, like making the American dream possible for more deserving people. This is work that I'm very proud of. You can use your explainability techniques not only to quantify the impact of each variable in predicting a loan default, but you can also look at their contribution to things like approval rate disparity between the white non-Hispanics and everyone else, or the men and the women, or the elderly and the young people. And so once you're able to very accurately quantify these things, then you can start to play around with their influence and their values by using additional mathematics from competitive game theory. We can set up a Nash equilibrium between the opposing forces of fairness and accuracy, and generate a front of models, each of which has different degrees of fairness and accuracy, and then look at the trade-offs that those models generate. And so what you see here is credit score is contributing pretty significantly to approval rate disparity between the African American and Hispanic populations and the white non-Hispanics. It's also really important in the model. It's producing quite a bunch of predictive power. So taking that credit score out of the model would result in a model that doesn't make very good predictions. So what do? The Equal Credit Opportunity Act allows you to just say, oh, well, that's life, and justify this as a business necessity. We wanted to do something more. And so we found a way to attenuate the impact of these disparate impact-causing variables using adversarial training and generate a more fair model that gives up very little accuracy. And so I'll show you some more details on that. So our original machine learning model achieved a very high AUC. It's the thing in the circle in the lower right, okay? And the series of models that our fairness method generated, our less discriminatory alternative search generated, are along that blue line. So each one of those diamonds represents a new model, an alternative model that you could consider deploying. The yellow dots represent drop one alternatives. And so you can see, by removing the credit score, I end up with a very low precision, low AUC model. Okay, so what I'm going to show you, though, is that I can give up just a little bit of accuracy, that's that red arrow, and gain quite a lot of fairness. Okay, so the math allows us to not only quantify what's driving the disparity and what's driving the accuracy of each and every model decision, but it also allows us to consider all these different alternatives and make a better trade-off between these two kind of important factors. And so the result is a model that's just a little bit less accurate. Okay, I'm going to leave $1 million in profit on the table out of my $50 million business case. But as a result, I'm going to improve fairness quite considerably, about 30% in impact ratio. So 100,000 more people of color in homes next year as a result of this. So we think the math is pretty cool, and that you should use it to build credit risk models. Because if you have the right explainability and you have the right discipline around and the right tools, you can use them to build more predictive models that are more fair and transparent. So if there's 3 things that you take away from this talk today, the first of them is that machine learning does a much better job than traditional modeling methods for credit risk. The second is that if you have the right explainability, you can safely apply machine learning. And then the third is that with the right math and tools, you can use ML to make more fair and transparent lending decisions. So with that, we have 5 minutes for questions. Yeah.
So one quick question, right? Like some of these particular techniques are model agnostic and some are basically like model specific. And whatever, like if you take Shapley or anything like that. One thing in my experience, and like my experience has been more on the unstructured side.
Sure.
If I apply it on a neural network,
Yes.
the thing, what happens is that like I'm giving some inputs.
Yes.
But in the intermediate thing, whatever be my final basically thing, representation learning or some representation of that input is actually learned. And then based on that, the downstream task actually happens, although in the same thing, right?
Yes.
And I have this big dilemma that whether I should be explaining, what really explainability means
Yes.
in that particular context.
Yes.
Whether it is basically like should be attributed to the inputs or whether it should be attributed to the patterns that particular machine learns to basically like it.
Yes, I love this question. This is a very good question. So just to repeat the question, it's about oftentimes, I think, and tell me if I get this right, oftentimes you're not just looking at a model input and a model output, you're looking at a composition of models, some of which are building features out of some inputs, and then those models input features to another model, and then that model is transformed further by a function to generate a decision or an outcome. Where's the explainability? Is it in terms of the original inputs, the inputs to the intermediate model, the inputs to the outcome? On what level are we doing explainability? There was a second question, which is sort of how do I understand what's happening in the internal layers of a neural network? Are my learning representations there that I can explain? And so what's cool about the methods that we use is that we can answer that explainability question at any level of the processing. And we can look at the composition of diverse models. I can take a tree-based model and ensemble it with a neural network, and then pass that through a smooth DCDF to get a probability estimation. And I can still explain through the whole chain, or I can look at pieces of the chain and explain those. So the right mathematics allows you to do explainability of these very diverse predictive functions. And so you can investigate each and every point in how a model score is generated.
Are you just focusing on residential mortgage loans with your product? Because that's where you get all the demographic information. Are you looking at small business loans, different types of loans?
That's a great question. So part of what we focus across the spectrum, and I'll just go all the way to the beginning. So unfortunately, here we go. Unfortunately, in some of these other products, you don't get the demographic information at the time of application. In fact, it's illegal to collect it, right? So you have to kind of rely on these other methods to infer the demographic information. And so the CFPB and a number of the different regulatory bodies have endorsed a method called BizG, which was developed by RAND, that allows you to guess at someone's race and ethnicity from their last name and their zip code. And so in those cases, that's the best that we can do, unfortunately.
I know for the mortgage world, you get all the data.
That's right.
So you're guessing at the other.
Yeah, unfortunately, that's all we could do. If I could collect the data, I would use the ground truth. Yeah. Yes?
How do you measure fairness on that last question?
Yeah, that's a very good question too. This is the impact ratio. So it's the approval rate of the protected class divided by the approval rate of the white non-Hispanic. Or sorry, white non-Hispanic. Where is it? Here. So that's commonly referred to as the impact ratio. You can plug in any metric to this method. It's a adversarial training method that relies on another model that is trying to predict the race and ethnicity or the gender on the basis solely of the first model score, and then uses that to penalize the first model's training. Yeah.
How does explainability guide this calculation?
Well, so at the end of it, I'd like to know what's driving the fairer model to understand from a safety perspective whether or not what I just did was a good idea. And so at the beginning, you want to look and quantify sort of the impact of each variable on both the model accuracy and the fairness outcome. And then after you run this thing, you want to be able to see, well, what changed from the model's perspective. And then check that against intuition and do the rest of the analysis that's required to validate the model. And so my view is that without the right explainability, you wouldn't be able to do that last part. And so you wouldn't be able to trust the more fair alternative that was generated by this method. Does that make sense? So they're sort of like hand in glove, even though they're not the same. Yeah?
Sorry, I'm not very technical in this space. I'm going to ask maybe a simple question from my perspective. Right?
Sure.
The last session we were talking about, especially when it comes to multidimensional spaces and these deep neural networks, some of this might be beyond a human brain's ability to understand and explain.
Sure.
And here we are in the session right after that, and we're saying, but yeah, you can. And chaining all of these complicated machine learning tools together are still achievable in terms of explainability.
Yes.
I feel like we're contradicting here, and perhaps our earlier speaker could enlighten us in terms of is this in alignment with what we heard in the previous session, or in contrast to it?
Humans are not doing the explaining.
Right.
Comprehension.
Right.
And humans couldn't do this, but his method.
Right. So the question was, deep neural networks are really complicated. They contain all of these interactions and hidden layers, and there's these dot products and different weights going on, and feedback functions and sigmoids. And what do I think about these activations? How can a human take a look at that system of equations and understand it? And the answer is the human, just looking at the system of equations, can't. What you need is a mathematical method of analyzing that system of equations so that you can reduce the impact or project the impact of the model onto the input variables so that you can understand them. And fortunately, we have the tools of the path integral and the partial derivative to help us with those things, even with very complicated functions. The problem with that is that those don't handle all types of functions, and so you need to extend them by using the tools of measure theory. And so that's what we've done.
The check in the system is the fairness indicator.
No, the check in the system is the analysis, the analytical proof, and the KPI, right? So you can prove mathematically that these methods are sound and unique, and then you can look at the performance and see empirically that they produce better results.
All right.
Measure theory method?
Our method of explainability. I'm happy to talk with you more offline.
So we do have to move on to our next session, but
Yeah.
thank you so much, Jay.
Thank you.